Hi class, this is Jo Charlton, and today we're going to cover chapter 2 in the Pearson book. I have two different classes that I'm teaching and they both have a different book. So my hybrid class is using the Essential Chemistry for Biology. This is the exact same material that my second class is using also. It's just presented slightly differently, so I'm going to, you can use either one. So the other thing you want to get ready before we start is going to be your study guide, and then we can fill it out as I lecture. Right. And then I need to click in the right place. Here we go. Okay, so basic chemistry. If you zoom in close enough to anything, you're going to end up at the chemical level. So cute little mouse, you go into the mouse ear cells, there's going to be atoms within those cells. So our first term is going to be matter. And matter is anything that occupies space and has mass. So if you feel like, wow, she's going too fast, I am probably going to go too fast, and you're going to have to just stop this video and rewind it so that you can write it down. I do recommend writing down the answers because there's something about the connection piece between the visual writing it down and getting it into your brain. So our first term is matter, and that's anything that occupies space and has mass. Matter is going to be found on Earth. And for Bio 105, it's found in 3 physical states, which are going to be solid, liquid, and gas. There's also plasma, but this is Bio 105. We don't go into the depths of plasma. That's going to be like a higher level physics class. And I'm not talking about the plasma in your blood. I'm talking about weird plasma. Okay, so anyway, we've got our definition of matter. And then our next term is going to be elements. So matter is composed of the chemical elements. And the definition of elements, these are going to be substances that cannot be broken down into other substances by. Now for Bio 105, there's going to be 92 naturally occurring elements on the Earth. And we're just going to look at those 92. There are actually some other elements that they've only seen like in a laboratory situation because they break down pretty quickly. So all of the elements are going to be listed in the periodic table. We're only going to focus on some of them, like carbon, water, H2O. So we'll talk about that more in a second. Here is our periodic table. So in this class, I'm hoping you can see my cursor, we're pretty much going to be looking at these first 4 rows. If you are a business major, you might like these elements because this is our money. We've got copper, we've got silver, and we've got gold right here. But pretty much we're going to look at hydrogen, carbon, nitrogen, oxygen, maybe some sodium, magnesium. This is potassium, calcium. So that's pretty much it for our biology class. Over here, chlorine. And phosphorus. So we're not going to look at the whole periodic table. So if you look, your first concept question, which I forgot to point out, was what are the 3 physical states in which matter can exist? So that was solid, liquid, and gas. So our next concept question is going to be what 4 elements make up 96% of the weight of the human body? So the answer to that one is found on this slide. So we've got oxygen. You do not have to know the percentages. So you've got oxygen, you've got carbon, you've got hydrogen, and you've got nitrogen. Now a memory trick for me is I like to make a word out of it. So I say C for carbon, H for hydrogen, O for oxygen, and N for nitrogen. And that kind of makes this word CHON. So if you remember CHON, those are the 4 elements that make up most of the human body. All right, so trace elements. Your next concept question on that first page asks you, what is a trace element, and are you able to name several of them? So trace elements are necessary in teeny tiny amounts. You don't have to know this particular number. Very small works for me. These are ones they're essential for life. If you do not have them, you're going to be in trouble. This lady is from a country where she was not getting enough iodine, and she's got a condition in her thyroid called goiter. So in the United States and other countries, they actually put iodine in our salt. Salt is usually sodium chloride, NaCl, but they add iodine to it as a necessary nutrient. So other trace elements are going to include these ones here. You may have heard of iron. If you look at your vitamin bottle, if you take a vitamin, you're going to have iron in there. You're probably going to have some zinc. So at least know 1 or 2 of those: iodine, zinc, iron. Iron is one of the ones you don't want to get too much or it actually poisons you. I think for a short time they were making gummy bear vitamins, and these little kids got a hold of them. You get a hold of a gummy bear vitamin, and the kid could eat too many of them, and it could actually kill the kid. So if you have any kind of vitamin that looks like a candy, make sure it does not have iron in it, so kids don't mistakenly overdose on it. Okay, so now we've got, if we march down our list of terms, we've got the word compound. So elements can combine to form compounds, and the definition of a compound is going to be a substance that contains 2 or more elements in a fixed ratio. So we've got NaCl, salt, which is what we dump on our food all the time. That is going to be a compound. And if you look at pure sodium here, and we look at chlorine, which comes as a gas, this chlorine gas is actually poisonous. This is a very soft kind of metallic-y butter. So somehow when you put those 2 together, it turns into salt. It's like mind blown. All right. So our next concept question on the study guide is, what is an atom? So an atom is defined as the smallest unit of matter that still retains the property of an element. So the example of sodium, again, it's kind of like a soft metallic butter that you can cut with a knife. If it's pure, that chunk is made up of sodium atoms. So the second part of that concept question asks, describe the basic structure of an atom, including the charges. So if we look, there's going to be protons and neutrons. So a proton is positively charged, and a neutron is neutrally charged. So it doesn't have a charge at all. It's neutral. And then we have electrons that are negatively charged. So I like to have my students do this silly hand routine where we start doing this and you say, this is my atom. Inside my atom is a nucleus. Inside that nucleus, there are protons that are positively charged. Also inside the nucleus is a neutron, which is neutrally charged. And then zipping around the outside, those are going to be my electrons. So if you want to pause the video for a second and just go through that silliness to help get it into your head, you've got protons, neutrons, and zipping around on the outside are going to be the electrons. All right, so where are we now? Now we are moving along on our study guide. Elements differ in the number of subatomic particles in their atoms. Subatomic particles, what are you talking about? Subatomic particles are just the protons, the neutrons, and the electrons. So you already know those names. So it's the number of protons, that's going to be the atomic number. That determines what element it is. And then you're going to have this mass number, and that's going to be the sum of the protons and the neutrons. I actually don't ask you to define that on your study guide, but so if we go here to the next slide, if we look at our periodic table, and I have another slide with the periodic table. If you have your book, the back of the book also has a periodic table in it. Of course, now I'm on camera, I can't find it, but it is in there. So we've got, and when we get into class on Wednesday, you can look up at the board and see, we have a big periodic table in the classroom. There's going to be, this is carbon. It's going to have this number on the top of it, and it's going to have a number on the bottom of it. So it's like that top number is the atomic number. This tells you how many protons carbon has. So carbon always has 6 protons. That number changes, or it becomes a different element. Okay, so carbon is always 6. And the mass number, this is the number of protons plus neutrons. So the mass number can change. So this number of neutrons can change, and we actually see that more often as we get lower into the periodic table. We also see it with carbon, but we're going to show you that example here in just a second. So the mass number can change because that's protons plus neutrons. The atomic number is only the number of protons. Now, this is when we can get a different number of neutrons, when we have something called an isotope. So this is the next term on our study guide. What is an isotope? It's an alternate mass form of an element. So they have the same number of protons and electrons, but they have different numbers of neutrons. So if we look at carbon, for example, most of the time, carbon is at carbon 12. This is the most stable form of carbon. So you've got 6 protons, 6 neutrons, 6 electrons. The protons, remember, are positively charged. The electrons are negatively charged. So everything's all cool and groovy. We've got positivity, negativity, everything's balancing out. In carbon 14, which we will talk about in a few slides, we actually have 2 extra neutrons. So these tend to be less stable, and occasionally carbon 14, we're going to talk about this in a bit, breaks down into carbon 12. But an isotope definition is an alternate mass form of an element. So when you have more neutrons in that nucleus, the nucleus is going to decay, and it's going to give off particles and energy with that, and that's how we get these radioactive isotopes. So on our study guide, we ask on the very bottom of the first page there, name 2 ways in which radioactive isotopes are used in biology. So we've got something called a PET scan. This is a medical scan where you can see which areas, say, of the brain are active. Archaeology, we can use carbon-14 dating. We'll talk about that in a second. Molecular biology, you can label DNA and you can find out like where it goes. Not really where it goes. This is one of those things where I'm on camera and I'm saying the wrong words. But you can label DNA and see it in different bands in a gel kind of situation. We're going to be looking at that later in a lab. So you want to know at least 2 ways in which radioactive isotopes are useful in biology. Bombs is not going to be an acceptable answer. So I have had somebody put that on an exam. Bombs. I'm like, no, that's not really a good thing. So if you have uncontrolled exposure to radioactive isotopes, this is going to harm organisms, damages the DNA. If we look 1986, which was before many of your times, we had this accident in Russia, the Chernobyl nuclear accident, where one of their nuclear power plants had a meltdown. This is still very, very radioactive today. And then 2011, you might remember this one. There was a huge tsunami hit Japan, this town called Fukushima, and they also had a nuclear meltdown at their nuclear power plant. So this is kind of a map showing you the fallout from that, like after 3 days, the radioactivity, the dosages of the radioactivity, and it did actually hit our west coast. This area in Chernobyl is still very radioactive. There are some times where they let researchers go in there and test things, and it's kind of bizarre. It's like a ghost town, and I think it was Nature Nova on PBS did a show about it, and they sent some people in there, and they were actually looking at wolf puppies because all the humans got the heck out, and it's like a ghost town where everything that they were doing is just left as it was, and they got out. So now, like, the plants are starting to grow into the houses, and there are these wolves that have moved into this town, and they were checking the wolf puppies to see if they had mutations and stuff. The wolves were still living. They don't know if the wolves are having a shorter lifespan or if they have less puppies. Another study that was done in Fukushima was looking at butterflies and moths, and they did find that a lot of the butterflies, moths that they were looking at had mutated wings, and they were not able to fly. So you don't want to hang out with radioactive isotopes too much because it damages your DNA. Okay, remember how I kept saying, I'm going to tell you about carbon-14 and how it breaks down. This is the slide that does that. So for the most part, there's a stable ratio of carbon-14 to carbon-12. There's like this certain ratio that's in the environment. And if you're alive and you're eating your food, you're going to have that same ratio in your body as the environment does. But now you die, you crawl into a cave somewhere, and your bones are just sitting there, and then 10,000 years later, some archaeologist finds you, and it's like, whoa, here's a human body, or here's a bunch of bones. How old is this? Did this die 6 months ago? Did it die 10,000 years ago? So what they do is they take a sample of whatever they find that's organic, that's used to be alive, and they check the ratio of carbon-14 to carbon-12, and knowing how carbon-14 decays every, it's 5,568 years, half of it is going to be gone. They can actually tell how old the bones are that they just found. So carbon-14 is only good for dating to 50,000 years. So if you're at an archaeological site and you're looking at something that's 70,000 years old, carbon-14 is not going to work for you, but there are a lot of other radioactive isotopes that have much longer half-lives. That means it takes it a lot longer to break down, and they can use those to study other things. All right, I'm doing too much hand stuff. It's just so weird doing this. Doing all of this on a video instead of in front of you. Okay, so here we go. Next slide. So electron arrangement and then the chemical properties of atoms. So remember how we had our nucleus with the protons and the neutrons in it, and then we have electrons zipping around each other. So when one atom comes into contact with another atom, what is the thing that's going to interact first? So, okay, I'm skipping around in my own study guide. If you're on page 2 now, you've got which of the subatomic particles is responsible for the chemical bonding reaction behavior of an element? That's going to be the electrons, all right, because those are on the outside. That's what's when one atom comes into contact with another. The electrons are going to meet each other first. All right, so on the top of page 2, it's asking you to draw the electron shells of the carbon atom. How many electrons does carbon need to fulfill its outer shell? So we are going to very, very basically get into electron shells. We are not going to go further into depth like you would in a chemistry class where we start talking about electron orbitals. You can take that in chemistry class. This is just basic chemistry for Bio 105. So it says it wants you to draw carbon. So this one here, the second one over, is actually carbon. So if you look in the center, you have protons and neutrons. Remember, we have our protons and neutrons. So just kind of draw a little blob of protons and neutrons in the nucleus. And then we're going to talk about electron shells. So I might zip back and forth between the next 2 slides. So hang on and let me explain the periodic table to you. Okay, so here's the periodic table. Why is it arranged the way it is? Why did they put like this weird step here and then this weird step here? So they wanted to arrange the elements in a way that their properties were the same. So if you go like up and down, so columns equals a group, and elements in a given group are going to share many chemical and physical properties. So they wanted to keep those guys together. So we have these rows, which are groups. I said it backwards. Columns are the groups. And then if you go across, we've got these rows. Now, if you look, our first row only has 2 elements in it, hydrogen and helium. So that row actually coincides with the electron shell. Okay, so your first row has 2 elements, so that's telling you how many electrons go in the first shell of an atom. And then our second row, how many elements do we have here? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so shell 1 is 2 electrons. It only has 2 in that row. Shell 2 has 8 electrons, and shell 3 has 8 electrons. Shell 4 has 18 electrons, and this is where we get into these crazy things called orbitals, and we're not going to go that far. We're just going to talk about these first 2 rows. So now if I go back to the picture of carbon, and we go back to our study guide, it says draw the electron shells of the carbon atom. So we've got carbon here with the protons and the neutrons in the middle. And then we've got that first shell, and that has 2 electrons in it. And then the outer shell has room for 8. See if I can do 8 with my fingers. 8 electrons. So if we go 1, 2, and then 3, 4, 5, 6, we don't quite fill that outermost shell. So I'm going to flip back to where carbon is in the periodic table. Okay, so how do I know how many electrons carbon has? We've got 1, 2, 3, 4, 5, 6. Okay, so 6 is actually the atomic number of carbon. It's how many electrons it has. So we know that the first shell has 2, and then we've got 1, 2, 3, 4 in the second shell. So I'm going up again. So we've got 2 in that first shell, and we have 4 in the outer shell. Now the filled spots, the yellow spots here, mean that an electron is there. When you have a white hole with black around it, that means that it's empty. Okay, so how many electrons does carbon need to be fulfilled in that outer shell? We can count. We need 1, 2, 3, 4. How else can we do that if we're just looking at the periodic table itself? I know we have a whole bunch of psych majors, so let's talk about it with our feelings, okay? So carbon is kind of sad because it doesn't have its outer shell fulfilled. So how many electrons does it need to be fulfilled? You can actually count how many spaces till you get to the end of the row. So see how there's 1 space, 2 space, 3 space, 4 space? So now you know carbon needs 4 electrons to be fulfilled, have its outer shell filled. So if we look at oxygen, that's going to be O. How many electrons does oxygen need to be fulfilled? If we look at this, 1, 2. It needs 2 because it's 2 spaces away from the end. Okay, these guys on the end, they are completely fulfilled. So what are you talking about being fulfilled? Talking about this outer electron shell, how every element really wants to have that outer electron shell fulfilled, filled with electrons. It's interesting because, okay, I'm looking at my next question. Our third question on page 2 is going to be, what types of elements cannot form chemical bonds with other elements? So if we look at that, these guys on this side, they have their outer electron shells completely filled. So they do not need to interact with any other elements because they are totally filled. So this is helium, neon, argon, krypton. These guys are all gases, and you never hear like helium chloride or neon chloride. It's just neon. It's just helium because they are by themselves, their outer shell is fulfilled. All these other elements, they are not fulfilled. So in order to be fulfilled, they want to either steal or share or give away electrons so that their outer shell is fulfilled. So that's what we're going to talk about next, how these elements fulfill their outer shell with electrons, and they do that by forming chemical bonds. Okay, I am at 29 minutes, so I'm going to take a break and I'll do another movie because 30 minutes is long enough.